Okay, well, it's a great pleasure to welcome today's speaker, Stratos Petroloudis, who is going to tell us about some D0 brain physics. You have the title, and he's speaking to us from Regensburg. Thank you, Stratos, for joining us. I'll hand over to you.
Thank you for the invitation. First of all, let me share my screen. Start sharing my screen. Can you see my slides?
Yes, absolutely.
Okay, then I guess I'm good to go.
Yes, please, yeah.
Okay, good. Well, again, thank you for the invitation. And I'm going to talk about joint work with my collaborators appearing here in the bottom left on the page. And the talk is going to be based on these three papers that appear here. So there are three different topics, but all of them, they concern the low temperature regime of the D0 brain matrix models, something that I'm going to discuss. So I don't know how the format of the seminar is, but if something it is unclear or you want more details, just feel free to interrupt and ask questions. Good. So the question why I am interested in low temperature is fairly simple from to first order. So at low temperatures, we have a well-known analytically known gravity duals. So we have analytical geometries about these models. And the matrix character of these models has some non-commutative features, which are usually interpreted or we are hoping to interpret them as quantum effects, capturing quantum effects. So in this way, I want to ask the following question: if ultimately, if we can use these matrix models at low temperatures to find imprints or traces of quantum gravity. Of course, this is not an easy question because we don't really know what to expect from quantum gravity, but a more easy question that I want to ask and answer today is what happens when I'm thinking about gravity classically. So I will discuss how this is realized later on. But for the moment, the low temperature regime is motivated because we have analytically known duals, and then we can ask relevant questions regarding these models. So this is the plan of the talk. I'm going to define the models in the beginning, then I'm going to discuss a little bit the idea of holography and the connection with gravity. Then I'm going to discuss the confinement phase in D0 matrix model and what does this exactly mean and how this is understood from a gravitational point of view. And furthermore, I will proceed by simulating and doing several tests at low temperature. And one of these tests would be to compare between the eternal energy of the black zero brain, a specific geometry, with the energy of matrix models by performing simulations. And at the very end, perhaps I will have time to comment on the role of the gates symmetries in these particular models, if they are important or not. So let me start by introducing the model. So it is given by this axiom here, which contains several fields. So the color-coded fields here are actually matrices, and these X matrices are bosonic Hermitian matrices, which run from 1 to 9. On the other hand, I have 16 fermionic matrices, given by blue color, or psi. The covariant derivative appearing in the kinetic terms acts on observables like this, And one important thing is that the 't Hooft coupling, which multiplies the whole action, has units of energy cubed, which makes this theory non-conformal. And because we are in one dimension, we are actually having a matrix quantum mechanical model. Now, this particular model can arise as a dimensional reduction of different theories, basically on theories living in different dimensionalities and having different supersymmetries, such as those Young-Mill theories. And in the context that I'm interested in, it first appeared by DeWitt, Hoppe, and Nicolai in '88 to regularize the 11-dimensional supermembrane. Of course, these models were also in the literature before that to trying to understand supersymmetric quantum mechanics. But in 11 dimensions, it is a little bit special because something like 8 years after the work of DeWitt, Hoppe, and Nicolai, Banks, Fissler, Seskin, and Saskin, they proposed that this model should be a non-perturbative approach or definition of M-theory. And then Izaki, Maldacena, Sonnenschein, and Yankelowitz, they put this model in the context of Gates gravity duality, and they proposed that this is dual to a certain black zero geometry near the 't Hooft limit. So in today's talk, I'm going to focus exclusively on these last two topics, and the reason is because I'm mainly interested in gravitational physics emanating from string theory. And for this, let me start to give some more information and motivate a little bit the Gates gravity duality in string theory. So the usual consensus is that at one hand you have a black p-brane in certain superstring theories, and via the work of Maldacena, this is dual in p+1 dimensional Young-Mill theories, which contain dp branes plus strings. Now, in this talk, I'm going to set p equal to 0. So here I will have a black zero brane in type 2a string theory, and here I will have a 0+1 dimensional matrix quantum mechanics. And this is actually the model I motivated in the previous slide. Now, since we are outside the context of the usual idea CFT, I want to discuss a little bit how the idea of holography is realized in this model. So, because I told you that the 't Hooft coupling has units of energy cubed, one can actually construct an effective dimensionless coupling by dividing with appropriate powers of energy. And the idea behind these matrices X, for example, that appear in the action, is that diagonal elements given by this color green, they actually give information about the positions of the D0 branes, and non-diagonal elements, they concern open strings stretching between the two D branes. In fact, you can think, if you are more familiar with string theory, you can think this the indices of matrices as the Shand-Patton indices of the string theory. So, for example, the index 2n will concern a string stretching from the second brane to the nth brane here. So this one. So this is an interpretation due to Witten and goes back to 95. And because I have 9 of these matrices, and because each of these matrices, it gives me information about one dimension, having 9 of those, I construct information about a 9-dimensional space. And the idea is that if I know the conducts of the matrices, I know how these D0 branes are spread in this 9-dimensional space, and how the open strings, if I have strong interactions, or long strings, or small strings, etc. Now, again, one more information that I can deduce from this is that if you see the potential term for the bosonic matrices, it has this structure, which if you do the commutator, it has a structure which is similar to the theory of and of course, the idea is then that how do these D0 branes are spread into this potential. Now it's quite easy to see that the minimum is when all these D0s are in the center, so when x naively is 0. And the question that somebody can ask at this point via doing this holographic idea is that what does this correspond to in the gravity side? So what does it mean to have n D0 branes packed at a certain point? Now, before answering this question, I want to motivate and introduce basically another matrix model, which is a deformation of the previous one. So the difference is that the name now is not BFSS, but is BMN by Berestein, Maldacen, and Nastase, like 4 years after BFSS. And the idea is that you keep the BFSS action the same. Here, the first two terms, which are this one here. And then you add deformation terms given by these expressions down here. Now, all these, the two deformation terms, they concern a deforming parameter, which is called mu. And this can be thought of as mass terms for bosons and fermions by multiplying quadratic fields, quadratic terms. And you also have a cubic term, which is known the Myers term. And importantly, if you send mu to 0, if you consider the massless case, then you recover the BFSS. Now, the difference is that in addition to the same vacua appearing in BFSS, now you have a new class of vacua, because you can write the bosonic potential like this, and it is fairly simple to see that if you assigned these matrices with SU2 generators, then they minimize the potential. Is there a question?
Yeah.
Yes.
So how much supersymmetry does this preserve, the BMN model?
So the BMN model has half BPS states.
So
it
total
has n equals 16 supersymmetry, real n equals 16.
Yes.
N equals to 16. Okay. And can you think of this as dimensional reduction of some other model?
Yeah, actually, this is super Young-Mills theory reduced over the sphere, over S3, I think, if I remember correctly. So if you compactify super Young-Mills theory in 4 dimensions over a compact manifold S3, then you get precisely this model.
Okay, thank you.
Yes, you're welcome. And now the one more interesting thing is that so these SU2 generators, they construct another vacuum, which is the fuzzy sphere. And depending on the representation of SU2, you can have many different fuzzy spheres. So Denjo spent a lot of time, I think, studying these objects for BMN. And one more ingredient is that you have an explicit breaking of the symmetries. So previously you had SO9, but now you have SO3 times SO6, and you can easily see that by looking at the indices that run, for example, here from 1 to 3, and here from 4 to 9. So you have an explicit breaking at the level of the action. And yeah, so today I'm going to focus exclusively on the vacuum appearing here. So when all the D0 branes, they are localized in one space-time point and they don't spread to form fuzzy spheres. Now I'm going to go back and answer how should I think about this vacuum when I am in the gravity side. And Einstein's theory tells me that if you put a lot of matter or a lot of dynamical matter in, and you press it in one space-time point, then you distort the geometry of the space-time. And then you create some sort of black hole. Now, these D0 branes, they are dynamical, they have energy, and they have tension. So if you pack them on one space-time, you create something which is known by the name of black zero brane. And it is a solution of 10-dimensional supergravity, and specifically type 2A supergravity. Now, this solution is valid only at strong coupling and at low energies, which is motivated by this effective dimensionless coupling. Low energies should always correspond via this mapping here to strong coupling. So the metric is given by this equation here. You have an S8 sphere here, and you have the sourcing functions, and you also have a horizon given by R0, and this horizon is assigned with a temperature. And of course you can do thermodynamic analysis, you can find the energy. The energy scale is like n squared, some funny power of lambda, because lambda is dimensionful and not dimensionless, times temperature to 14/5. You can also find, using the first law of thermodynamics, entropy, and two more important parameters that control the regime of validity is the curvature of this geometry given by whatever is multiplying this sphere here, which you can express everything in terms of this dimensionless coupling G effective appearing here. And another thing is the dilaton on the horizon, which again you can find expressions in terms of G effective. And now, based on a figure appearing in this paper by these people here, I can ask some interesting questions depending whether I want to study high energies, low energies, small n or large n. So here in the y-axis it is log of n, and in the x-axis is log of 1 over energy. So what I can do now is I can demand my solution, this metric here, to be valid by requiring the dilaton to be small and the curvature to be small. And what I do is I'm constraining my system to rely into this region here. Now this is the usual consensus about these geometries, but here you see that even if you are in relatively large n and you want to study very, very low energies, there should be a transition point that maps you from this type 2A region to the M-theory region. So to motivate a little this a little bit better, I'm going to define, to use the usual definition of the type 2A string theory, which is defined. Sorry?
I had a small question.
Yes.
So I suppose these are this preserves some supersymmetry. Why is the temperature? Typically, temperature vanishes for supersymmetric black holes.
Sorry, can you repeat the question? Because
typically for supersymmetric black holes, temperature vanishes. I suppose this also, zero brane also preserves some supersymmetry, but I also see some temperature.
yes, here the thing is here that it's not. So this is the solution of BFSS, which doesn't preserve any supersymmetry.
I see.
Yes, so this is not the BMN, in other words, if this helps you to understand this better.
Okay, so this is not stable also then.
So it's not what?
This is not stable also then. Typically,
What
Hawking radiates.
What do you mean by stable?
Extremal black holes are stable, they do not Hawking radiate.
Yeah, in certain regimes it can radiate, but it has positive specific heat, if you wish. You can calculate the specific heat, and indeed it is positive. So I would say it is stable.
Okay.
I can take noise.
In the previous slide,
Yes.
yeah. How did you get these numbers? 7.41 for the E and.
Yeah. So this concern relatively. So this means that you should take, for example, most easily is if you understand this entropy. So here you have a spherical solution, okay? So you have a higher dimensional sphere. And then you can ask the following question. If I believe that Hawking's, so the Bekenstein law or the Hawking-Bekenstein area, the entropy law, let me say, which goes like the area over 4, is valid, then you can calculate the area that this geometry spans. And this means that you have to take into account the area that this S8 sphere constructs. And if you are very careful with all the pi's and all the cancellations that taking place, then you get this 11.52. Okay? It's, yeah, thank you. So let me go back and try to understand now how can I transition from one point to the other. So for this I have to define string theory as usual, which is M theory compactified on a circle S1. And the radius of this circle is related with the string coupling, which is further related with the dilaton, and the dilaton itself I can relate with the effective coupling I saw it before, which is lambda over energy cubed. So by keeping n, taking n to be large and keeping lambda fixed, I can ask questions to very, very low energies, which means that the effective coupling will be large, and tracing back, I get a very large radius. So this means that the compact circle starts opening up, and I should not ignore this compact dimension at very, very low energies. So in other words, I can think of it like this. So suppose that I have a small circle, then I increase the coupling by taking lower energies. The circle is increased, and I can further increase the circle by going to even lower temperatures or energies. Now this very naively should correspond to flowing from this region to this region and going either to this matrix black hole regions, which is, I think up to now nobody has any idea of what is going on there. So, okay, now if there are no further questions, I would like to switch to simulations and discuss how we can simulate this and extract physics. Okay, so the idea is that we can put this model on the lattice because we have just one dimension. And we can borrow techniques from, the well-developed techniques from lattice QCD community, and we can perform a Monte Carlo simulation of this 0+1 dimensional matrix quantum mechanics. So, because I have just only one dimension, and this is usually taken to be time, when I want to discuss Euclidean or thermal physics, I compactify this, and the circumference is given by 1 over the temperature. The parameters that I can adjust is how big this circle is by adjusting the temperature. N will give me the size of the matrix. S will be the number of points that parameterize my lattice. And then I want to take the large N limit. So the large N limit should be the classical limit. And based on the interpretation that I gave you before, that diagonal elements correspond to D0 branes, locations of D0 branes, the way they spread in R9, then by taking the large N limit, what I do is I construct more and more information about how these D0 branes are spreading into R9. And in this way, when I take the very large N limit, I have a classical object, I have a classical geometry, and it is the geometry I showed you before. Now, the way these D0 branes are spreading into this space give me information about certain geometries, and one way to capture how these D0 branes are spreaded is the Polyakov loop. So the Polyakov loop is defined by this expression. You take the trace of the path ordering of the exponentials of the Gates field, and on the lattice it is just a sum over the phases of the Polyakov loop. So, and the way these phases distribute on the lattice give me information about how these D0 branes are spreading. Now, the Polyakov loop is U1 invariant, as can be seen by here, and restoration or breaking of this U1 symmetry signals a phase transition, and this phase transition is known as confinement to deconfinement transition. And to build a little bit more intuition from the conventional holography, I recall what is the consensus of ADS 5 crosses 5. So here we are in the gravity side, and whenever the energy and the Polyakov loop is 0, this I identify as confinement phase, and it is interpreted in this specific example as a graviton gas. While on the other hand, when the energy is non-zero and the Polyakov loop is around 1/2 or bigger, I am in the deconfinement phase of the system, and this is usually related with black holes. So two very nice papers that you can find all this information is by Maku, so the big review of ADS-CFT. Witten, Sandborg was the first discussing this problem in ADS-5 in super Young-Mills theories, and it is nicely explained in Acharoni, Marsano, Minvala, Papadodimas, and Van Ramstok. Excuse me. So now, how do I see signals of this in the lattice? Here I have the Polyakov loop in y-axis, and on the x-axis I have the Monte Carlo time, or the Monte Carlo trajectories. And in the up figure, I have a simulation which starts from around 0 Polyakov loop with some fluctuations, and at some point it transitions to around 1/2. So this is something that I identify as the deconfinement phase, while on the other hand, in the bottom figure, I have exactly the opposite. I have something starting from 0.5 and then transitioning to around 0, taking account into fluctuations. Now, the one mild problem here is that the gravity theory predicts always deconfinement for non-zero temperature. So in other words, you see that from the expression of the energy, then that for non-zero temperature, you cannot have zero energy.
Question?
Yes.
Sorry, I'm not familiar with Monte Carlo time. What is this?
So basically with Monte Carlo, what you do is every time you're solving the problem, and every time you're solving it, you are registering a trajectory. So suppose that I want to to find the Polyakov loop, the value of the Polyakov loop. Mm-hmm. I solve it once, and then I allow the system to evolve a little bit, and then I solve it again, and then again, and then again. And this creates this the so-called Monte Carlo trajectories. So each time you're solving, you're getting a number, you're classifying, you're registering this as a trajectory. And this is what usually is thought of as Monte Carlo time. At least this is how I understand it.
So it's like number of runs, something like that.
The Monte Carlo is also, you can think of it in terms of a discretized Boltzmann type equation, and the Monte Carlo time is that time in the Boltzmann equation.
Yes.
I see, but here time is periodic since you're considering some finite temperature beta.
Yes.
I see Boltzmann time. Okay, maybe I should think a bit more. Thank you.
It's you shouldn't think of it as a, well, by the word time, different people can refer to different things. It's not something a physical time, let me say. I wouldn't say it's physical time. It's just an artificial time that you introduce, which evolves some sort of evolution of your system, and then you see how the system evolves compared with this time. But this is not the inverse of temperature you are thinking of.
See. So, I mean, can I think that with this increasing Monte Carlo time, I'm approaching the vacuum more and more? Would that be a correct way to think, or no?
The approaching what? The vacuum?
The minimum of the theory.
I don't know. I don't know.
I wouldn't think so. You're approaching equilibrium. If you think of a system that you started off and you have an equation, you want to treat the exponent e to the minus the Euclidean action as a Boltzmann weight. You want to probe that Boltzmann weight by using a Boltzmann equation that relaxes to equilibrium.
Okay.
And once you've reached that equilibrium, he's reached equilibrium up in the top diagram or in the bottom one, it fluctuates around that equilibrium solution. And the time is just a fictional time associated with this artificial Boltzmann equation that you introduced to simulate your system.
I see. Okay. Thank you.
Thank you for the comment and the question. So here there is a small puzzle, as I mentioned, that gravity predicts always deconfinement, so predicts only this picture, but we observed also this kind of situation. And first, what it is important is to show that this kind of situation survives when you take the large n limit, because the gravity theory is only valid in the large n limit. So I have to make sure that what I simulate and what I get survives when I extrapolate to the large n. So this is what I want to show in this slide. So I have three different observables that I'm plotting, but you have to pay attention only into the red one, which is the energy, and the green one, which is a Polyakov loop. So in the left side, I have large n extrapolation at fixed temperature and at fixed lattice points. So here you see that the energy does not go to zero, but the Polyakov loop does go to zero. And on the other hand, on the right side, I do continuum extrapolation at the same temperature, but now keeping n fixed. Now, on the other hand, it is not the Polyakov loop that goes to zero, but it is the energy that does go to zero. So different observables have different sensitivity in the large n and continuum. And this, now I want to ask the question, what should I choose? Am I in the deconfined phase or in the confined phase? Now, if I would be in the deconfined phase, I should have at temperature 0.2, I should have this particular number. So the energy should be around 0.08, somewhere here, and the Polyakov loop should be around 0.5, which is somewhere here. But obviously, when I combine both, I have to conclude that I am in the confined phase because the energy goes to zero and the Polyakov loop goes to zero when I combine the large n and continuum extrapolations. So to understand this a little bit better, I have to go back to what is known already. And this is the situation of ADS 5 crosses 5, and I have to build some motivation from this. Now, again, as it is explained nicely in these two papers, the phase diagram of the n=4 super-Yang-Mills theory is given as in terms of gravitational data, which in very high energies, well, in relatively high energies, you just have one saddle in your partition function contributing. This is the big ADS black hole, filling the whole ADS. As you lower the energies, you have an unstable phase, which is known as the small Schwarzschild black hole, which is localized on S5. As you even lower down your energies, you are hitting a point where a Hagedorn transition kicks in. And even below that, the only available saddle is a graviton gas confined in ADS spacetime. So now I want to play the same game with my matrix model, and I want to motivate that something analogous happens also for this case. And but the idea is very similar, but a little bit different. So again, what we are proposing is that in relatively high energies, we have one available saddle. This is a black zero brane. And as we lower the temperature, we have something that we believe that it is an unstable phase. We don't have proofs of this, but we have some hints. And this unstable phase is a black hole localized on this X11, so this along the compact circle. And below that, below these energies, we have an 11-dimensional graviton gas, which is in 11 dimensions now. So before, this whole picture was happening in 10 dimensions, but here we are proposing that there's also a topology transition from 10 dimensions to 11 dimensions. And here there are two transition temperatures. The first one is given by T2 and it goes by negative powers of n. I will explain in the next slide how to get this. And there is one more which goes with positive powers of n. So when I take the large n limit, the difference between these two temperatures should be large. And this means that the phases separating these two, the gap separating these two temperatures is not really sharp. So there could be a lot of overlap between one phase and the other. So now let me try to explain how to determine T1 and T2. So in a scenario, in a first order transition scenario, there should be, the Polyakov loop should have this kind of structure. The transition temperature can be located between T1 and T2. And T2 corresponds to the so-called Gregory-Laflamme transition or Gross-Witten-Wadia. And the idea is that you have a black string wrapping a circle S1. And at some point, this black string collapses to a black hole which is localized on S1. And you can ask, when does this happen? For which temperature this happens? And you can find that the temperature goes with inverse powers of n. And on the other hand, T1 corresponds to the minimum deconfinement temperature that I can have. And if I ask this question from the gravity side, and I am in very low energies, I can take the easiest possible black hole, which is a Schwarzschild black hole, and I can take it to have the mass of the Planck mass, and I ask what is the temperature of this. And what I find is that the temperature, of course, this is a naive bound, but I found that the temperature has positive powers of n. So when you take the large n limit, that's why there is this big separation between the two phases. So now I'm going to switch a little bit the subject and put it in more solid grounds and what is more well understood in the literatures. And to this end, I want to discuss one of the most precise tests of holography, which appeared in this paper by these authors. And what actually achieved this study here was to reproduce this kind of scaling by simulations of matrix quantum mechanics. So this is a prediction by gravity. And the question now is, can we reproduce this by using simulations of the matrix models I discussed before? And they managed to do that in the following way. So by extrapolating to the large n limit and the continuum limit, they got some points in different temperatures, shown by these points here. And then they did an extrapolation as you flow to 0 temperature. They basically did a fit, and they compared this fit with the gravity prediction, which is given by this black line. And you can see that the two lines approach to each other as you go to smaller temperatures. But of course, the difficulty was to go below this 0.4 point. And there are some technical issues why, and if you want we can discuss it later, but let us say that the BFSS model was not very good to go below 0.4. But now what we did, in addition to many other people, you see here that there are many deconfined states in the D0-matrix model, and there are many people contributed to this, and Denzo is one of those people. And one way to circumvent this difficulty of BFSS and probe even lower temperatures is to use the BMN model. So when somebody do the expansion of the energy, let's say the expansion based on what we expect by using string theory and supergravity arguments, we're expecting in the large n limit to be given by the first ratio here and quantum corrections appearing in this second ratio. So the only analytically known coefficients appearing in these ansatz here is this A0 and B0. So let us momentarily forget about this, because this would concern finite n physics, so quantum physics. And let us forget it because we are interested in the large n limit. So in the large n limit, only this term is relevant. And the authors of, so these people here studied how this specific coefficient, this specific term here gets modified if I include this mu in the BMN supergravity regime. So here you have a modification of this term, and F mu concerns an expansion of when mu is small. So what we did was to actually take the BMN model, simulate it, and compare with this ansatz proposed by these people here, and we found very good agreement with previous knowledge, and we managed to produce 3 more points when you go to very low temperatures. So the details of this paper are a little bit technical, and this paper appeared last Tuesday, so if you are interested you can have a look. It is known by this archive number. And the deviation between the gravity results and the simulation point can be understood as alpha prime corrections, which become relevant in higher temperatures. And I want to point out that here, in these 2 curves, there are actually 2 curves appearing, but they are very, very similar to each other, because for a mu equals 0.5, this deformation term is very, very small. So in this way, we were able to push the duality even to lower temperatures, which seem to reproduce the gravity results quite good. So now, the last topic concerns the singlet constraint and how important it is at low temperatures. And for this, I want to explain a little bit the Maldacena-Millikan conjecture. And it's a conjecture that says that so before tell you what the conjecture says, let me tell you what is the idea behind it. So the partition function of the Gates model is given by this expression here, where 8 is the Gates field, and when you find the equations of motion for the Gates field, you find a singlet constraint, which is given by this expression here. So this inserts a Gates symmetry in your model. But on the other hand, if you turn off the Gates field such that it doesn't appear, you don't have a Gates constraint. And what you do is you can actually implement this in the lattice by appropriate techniques. And the idea behind the conjecture is that the Hilbert space, the total Hilbert space, can factorize to the singlet Hilbert space and the non-singlet Hilbert space, which give rise to different regions of your spacetime. So I'm going to describe this conjecture in the language of string theory, very naively, just to give you an idea. So when you are interested in the singlets, you have to take the trace for these singlets. And because of the cyclicity of the trace, these states are thought to be closed strings, and closed strings are the strings that source your geometry, and they are supposed to live deep in the bulk, so to construct the black hole. On the other hand, with non-singlets, you don't have the trace, so you have open strings, and in principle, this string can reach all the way to the boundary. And in this paper, Maldacena and Milekin, they conjecture that at low temperatures, the difference between the partition functions of the gates and the ungates models, they are exponentially close to each other. So, of course, this is one way to motivate it. There is also another way to motivate it by quantum mechanics, which I'm not going to go there. And the idea now is, can we test that this is somehow reproduced by matrix models? And it is true for BFSS, which was studied by Berkowitz, Hanada, Rinaldi, and Vranas. And we also studied for the BMN model. And the BMN model, it has one more interesting characteristic, is that you can do perturbation theory using specific perturbative parameters. And we found that indeed it reproduces the conjecture, and it actually reproduces the perturbative results that are expected. So here I'm showing the points which are given by these dots here, and the red curve is the fit, a two-parameter fit over these 2 points, which has this specific form, and it is expected to be true in these 2 limits. On the other hand, with the blue curve, I give the perturbative analysis, which holds for large mu. So again, the BMN model has one other parameter, which is mu. So you can use it to do perturbation theory at small temperatures. And if you do so, you can find what is the contribution perturbatively of the lowest sector at small temperatures. And this is given by what I call here U1 sector.
Sorry, what did you mean by the U1? I missed.
The U1.
Yes, what U1 are you referring to?
Yeah, so the BMN, when you take the large mu limit, your theory breaks from, the symmetries break from UN to U1 times SUN. And U1 concerns the lowest possible states, and SUN concerns the more excited states of your theory. So this is so it is a characteristic of BMN in the large mu limit.
Okay, so that's the large mu limit is is at high finite temperature is just a Gaussian model.
Mm-hmm.
So
yes, that's right. You have a decoupling between the 2 sectors. So the Gaussian model decouples, and then you have the rest which doesn't contain mu. So in this way, you have two different sectors, and the U1 should be the one that concerns the Gaussian matrix model, I believe. I mean, we can discuss this, of course, more.
Sure. Let me.
Okay, so I guess I can continue.
Yeah, please.
Okay. So what I really want to point out here is that this blue expression concerns a perturbative calculation, so the contribution with the degeneracies of the states at lower temperature. And the red one is the fit, again at low temperatures, but not expected to be true in, in a large mu limit. But because with simulations we are testing things non-perturbatively, you see that how good the two approaches come to each other. So this is for mu equal 5 in the simulations, and you see how close they appear to be. So in this way, the non-perturbative method seems to reproduce the perturbative in this specific regime. And of course, if we would have higher mu, larger mu, I would expect the gap to close even more and more. Okay, good. So this brings me to the synopsis. So the closure of this seminar. I hope that I somehow motivated you that D0-matrix model are very interesting test examples for holography. So don't forget that these matrix models are defined on the world line, so it's just in one dimension, but somehow they have information about what is happening in 10 or hopefully in 11 dimensions. Then a stable confined phase has been observed for the first time. And of course, this remains to be verified by other people. There is an interesting possibility to probe contents of M theory, such as the membrane or the 5-brane, but these are a little bit more difficult and advanced tasks. We are not there yet. But what matters is to study in more details this separation phase between the two stable phase, which is the black hole localized on S1. In addition, I showed a precision test for holography at low temperatures, comparing gravitational black holes with matrix models, and on the other hand, the non-singlet constraint, the importance of non-singlet constraint tell us that maybe the gates symmetry in these particular models might not be that much relevant to have a good gravity dual. But of course, more studies are important, both confined and deconfined. And as a closing remark, I think it is also interesting to study higher dimensions. For example, there is this large D expansion in the literature, but simulations so far has not been done. And one interesting motivation is to connect these transitions with gravitational transitions. So with this, I would like to thank you for your attention and take questions now.
Okay, thank you very much, Stratus, and the floor is open to questions. Please. Lots of quiet applause in the chat.
Yes.
Can I ask a question?
Please go for it.
So in your latest paper posted this month, do you consider the ungauged matrix model or gauged matrix model?
Which paper you're referring to?
In your latest recent paper.
So there was one paper this Tuesday, you mean 3 days ago or 2 days ago?
Yeah, 3 days ago, I think.
Yes, on Tuesday we consider the gauged model.
Okay.
because
yeah, okay, sorry, yeah.
it was important to have a Gates constraint because we were comparing with the known analytically dual of the gravitational dual. So to keep things a little bit more solid, we use the Gates constraint. But in principle, if you believe the last statement, so this thing here, you should also be able to reproduce this by using the ungated model when you are in very low temperatures, right?
Okay. And in the study of that conjecture between gauged model and ungauged model, you said it's checked in the large mu limit. It's checked. I maybe missed something. Yeah, in this page. So that blue equation is the blue equation checked by large mu limit?
So what I tried to point out here is that here with the red, I define the difference of the energies of the ungated and ungated and gates, okay?
Mm-hmm.
And it is given by an exponential decay.
Yeah.
And on the other hand, I calculate the lowest set of states in the large mu expansion of the Gates theory only.
Okay.
And what I find is that it has this specific contribution when I consider all of the states, right? And the states of the Gates model, they give me this blue line here. And you see that Gates versus ungates and Gates, they are really close to each other.
Okay.
I don't know if this helps you more to your question.
Yeah, I think it's okay. Thank you. Okay, so basically we can believe this conjecture for BNN model, this result is saying.
Sorry?
Yeah, so can we, so in the BMN model, can we believe that ungauged model, so at least at low temperature, ungauged model is equivalent to gauged?
Well, that's precisely what this red line shows. It's so the proposal is that, you know, when you go to very low temperatures and you calculate gates versus ungates, or, you know, the other way around, you should see that these two partition functions are exponentially close to each other. So they're very, very close. So in this way, you expect the two models are almost equivalent to each other. And that's exactly what is shown here, because as you go to lower temperatures, given in the x-axis, you have an exponential decay. And actually this you can find for more observables. You can go beyond the energy, because here you have the partition function. You can differentiate the partition function to get observables, like, for example, also the free energy, or, you know, the trace x squared. So you're testing gauge invariant observables, and you see that when you go to low energies, the gates invariant observables and the ungates observables, they are very, very close to each other in this way. So I would expect, I mean, that's what we are suggesting, that it holds also for BMN.
Okay, thank you very much.
You're welcome.
Are there other questions? Hi, Werner. I see you've joined us. Werner, see you.
I wonder, when you look at the two curves, I would have expected them to get closer for large G. For that trilogy, but they are very close all over the range, and they look very similar. Do you understand that?
So if I understood the question correctly, because there was a lot of noise, you say that you are referring to this large D expansion?
Well, the comparison between gauged and ungauged.
Okay.
I don't understand why the curves look so similar over all the range. So do you have an area to calculate, let's say, the next connection?
So you mean for the, let me perhaps, the sound quality is not very good, so I cannot really, but let me perhaps give you an overall idea of, maybe I try to answer your question. So the idea proposed by these people is that take one model which has gauge symmetry, and take the same model and turn off the gauge symmetry. So these two models, they have different Hilbert space, and they motivate this conjecture by using string theory language, because when you take when you construct, so the question is how to construct a string using matrices, and the idea is to act with many matrices to some state. So when you act with many matrices to some state, if you want this state to be gauge invariant, you have to take the trace over this trace of a sequence of matrices acting on a state. Now, you can use the cyclicity of the trace to motivate that actually what you're building in this way is you're building a closed string. So this closed string should live deep in the bulk here, because this is what sources gravity. Closed strings give rise to gravitational physics in string theory. And on the other hand, when you don't take the trace, you have open strings, and these open strings can go all the way to the boundary. Now, I should have warned you all that this is a very basic cartoon, and it doesn't refer to a physical situation, but it is just to make things more easy. And then you have two different Hilbert space. The non-singlet Hilbert space gives information about all these strings on the boundary, and the singlet Hilbert space, which gives information about deep in the bulk. Now, what the conjecture says is that when you go to very, very low temperatures, the contribution in the partition function for the strings living on the boundary, it is not significant. It is not significant, so you can actually neglect it with an exponential error. And when you go to very, very small temperatures, you can almost neglect it such that you can exclusively describe everything with a gauged model or the ungauged model, depending on what is more convenient. One possible convenience is for the future, perhaps, as also these authors say, it might be easier to write a protocol for a quantum computer which does not have a gauge symmetry, because we don't know how to write gauge symmetry, how to give gauge protocols nowadays. I mean, this is beyond my expertise, but I understand that this might help to, simulate or feed in a physical model, ungauged physical model to a quantum computer. And what we did is actually to test this by performing simulations. I don't know if this answers some part of your question.
I've changed the microphone. Is it better now?
That's better, yes.
Enormously
okay.
better.
Sorry.
Yes.
Well, I wonder that the agreement seems to be better than expected. Your temperature does not seem to be so small. And I wonder if there's a way to calculate, well, the first term in the difference to get.
Yeah, there is, in fact, Werner. It's rather trivial to see it in this case. He is in the large mu limit, which means that he's a Gaussian model.
Yes.
If you take the trace if you take the partition function for a Gaussian model, it is trace of e to the minus something related to a number operator.
Yes.
So if I call this exponential, if I call it t to the number operator, at low temperatures, the only occupation number 1 or 2, if it's traceless, then your matrix says that you're forced to have occupation number 2 or something. So you only get t to a single power as your thing, and that's counting the dimension of the Hilbert space, the coefficient of it.
Yeah.
So the difference between the two has to be the difference in the dimension of the Hilbert space of the gauged and the ungauged in the t to the power in the occupation number 1 sector or occupation number 2 sector. So and that gives you the results.
Okay, thank you.
Right.
This is perhaps also related with a degeneracy, when you say occupation.
Yeah, it's the degeneracy is different. The coefficient of the exponential there is the degeneracy of that state, and the degeneracy counts the number of singlets if you're gauged, whereas it allows all states if you're ungauged, but the ungauged and gauged, there's one of them is a subset of the other. The gauge is a subset of the ungauged, so that
yes,
if there are singlets in that sector, then that's giving a contribution which is going like e to the minus the Hamiltonian in the lowest sector over beta, over t. It has to go like 1 over t.
Yes, indeed.
And it should be the energy of the lowest state.
Yeah.
Yes, indeed.
Yeah, thank you.
Are there other questions? If not, I will just stop the recording and thank Stratus again for a very clear seminar. Thank you.
Thank you.
Thank you for having me.